Good afternoon. I hope you're all doing well. Let's begin with the Parker Solar Probe. So, basic outline of the Parker Solar Probe, or PSP, is that over 7 years it's going to orbit the Sun um, 24 times and will cost about $1.5 billion, getting as close as 9.86 solar radii. So it will measure the particles coming off the Sun, the fields coming off the Sun, and as well as imaging the solar corona. It is named after Eugene Parker, who was the person who first predicted the solar wind and has done many key works in solar physics working on magnetic fields such as the Parker spiral, which is how magnetic fields emanate out from the Sun, and as well as the solar wind and such events as magnetic reconnection, which release large amounts of energy. On the right is an image of him, and on the bottom is a scale image. Well, the Sun is scaled to the distances to the Parker Solar Probe at closest approach in its final 3 orbits, and the Earth at the far right of the screen. So why? Simply put, practically, electronics. We are very dependent on electronics these days, and energetic particles that are charged emanating from the Sun can affect those through ways positively as the aurora, but also causing damage to the electronics. So airplanes, power industries are very important for this, as well as spacecraft and astronauts potentially more exposed to it. And then scientifically, there's also the fact that the Sun is a star. We want to understand stars because there are so many of them, and it is the closest one to us, so if we can understand it better, we can potentially understand stars as a whole better. So science goals for this mechanism, for this project. To determine the mechanism by which the particles, so the solar corona is more hot than the surface of the Sun, as you likely know. And so to determine the mechanism by which these high energy particles are kicked off of the Sun and end up in the corona, heating it, and as well as some ending up in the solar wind, which outflows from the Sun. And then, as well as in conjunction with this, they want to measure the transport of these particles away from the Sun. So the main challenges with this probe, with this mission, are first getting close enough to the Sun, given that we, launching the probe from Earth, have a given orbital energy initially. So then we need to decrease this energy and the speed that we have from this in order to get close enough to the Sun so that we can get the measurements that are desired. And then the second obvious one is temperature of the Sun. The corona is around 5,500 degrees Celsius, so getting instruments close to that without being fried up is a challenging task. So first, to get close to the Sun, we're going to use 7 gravity assists over the period, 7 gravity assists from Venus, which will gradually slow the speed of the Parker Solar Probe, and as such will reduce the size of the orbit. So we can see from this video that the first encounter just happened there, and then this will be at a 3-2 resonance. So next time around, the Parker Solar Probe will once again encounter Venus at the same location, and then the flyby after that will not be in a resonant orbit. So it will happen at right there, coming at the different position along its path. So the Parker Solar Probe would just be using these Venus flybys to adjust to reduce its perihelion distance. I will not be doing any further deep space burns, only some small trajectory correction maneuvers. And so you can see in the bottom plot below the video um, of the predicted orbits of the Sun that the distance versus the time from launch, and as you can see, both the aphelion and perihelion distances gradually decrease over time until a minimum at the 22nd orbit, where the 21st perihelion in the 22nd orbit, whereby the probe will have finished its final Venus flyby and will be as close as it's going to get to the Sun. So these Venus flybys use as mentioned earlier, use the aphelion speed to decrease the size of the orbit, and this is just the simple geometry, or the geometry of the problem. So the v minus infinity and v positive infinity are relative to the planet, and from conservation of energy in the frame of the planet, these are equal in magnitude, given that it's coming in and out of the well. But because the planet is moving relative to the Sun, these vectors can add through Galilean transformations, and as such, you can either increase or decrease the velocity relative to the Sun, where in our case we would be using a retrograde flyby to decrease the velocity. And you can see that these flybys actually get as close in the 7th flyby as 317 kilometers above the surface of Venus, so pretty close, but in the mission outline, they stated that this was not deemed to be any sort of risk to even need, say, light sensors to directly adjust the course of the probe when it is flying over Venus. So the other main problem being the temperature. So there are a few things the Parker Solar Probe will do to reduce that. First is most obvious, it's the thermal protection system called the TPS. It's a sandwich board made of carbon-carbon composite of on either side, with a carbon foam on the inside. And so then on the front facing side, you can see that white surface is the reflective coating to reflect as much of the radiation as possible, so as to not even have to deal with it, as well as solar wind and such, or that won't be reflected by. So then the TPS is 11.5 centimeters thick and 2.4 meters of maximum diameter. And then, so that will it will be at temperatures of around 1400 degrees Celsius, while the instruments behind it will be at about room temperature, so pretty good. Or a pretty stark difference between the two. So there's also the problem of powering the probe. So the solar panels because it's so close to the Sun, the solar panels will actually get fried if they are just left out, so they retract partially so that only an edge is able to see the part, or is exposed outside of the TPS. And then they also have a water cooling system, so channels of water running underneath them, which go up to these radiators, which are these black things right here, which then radiate that energy out into space. So because the Parker Solar Probe is at the Sun, it's too far away for us to be able to communicate in rapid enough time intervals, as well as it potentially being blocked in some cases by the Sun itself. So it has to make auto adjustments, so that it does not burn up. So to do this, it has these 4 solar limb sensors which just detect when any of them are exposed to the Sun, And then by detecting this, the reaction wheels will correct the rotation about the center of mass by spinning up and increasing their angular momentum in a given direction or along a given axis. And then by doing that, but from conservation of momentum, the rest of the probe will have its angular momentum increase in the other direction. And this is also key not just for passive correction, but because the solar wind is emitting a pressure on the probe, and because of the distribution of mass and the solar probe not being perfectly symmetric on its sun-facing side due to some instruments, the center of pressure is not in line with the center of mass, so that there is a torque, and so it also must correct for this torque with these reaction wheels. But because the reaction wheels can only spin so fast, it must do something called a momentum dump, which is it has thrusters on board, which it will fire for a burst moment to counter the angular momentum. And during this time, the reaction wheels will spin back down so they can get back to minimal speeds so that they can once again be spun up faster later. So instruments. The Parker Solar Probe has 4 main instrument suites for measurements of the electromagnetic fields, the solar wind in general, and as well as bursts of particles that emanate from solar events. And the ram facing side is the side that is moving into the solar wind, and anti-ram opposite. So the first set of instruments is the solar wind electron alphas and protons, called SWEEP. So it has solar probe analyzers spans, which measure both the electrons and ions in the solar wind. So span A has electrons and ion sensors, and it is on the ram side of the probe, so moving into the solar wind. And then span B only has an electron sensor, and it is facing away from the probe. And these two combine to give a pretty much complete view of the sky, other than what is blocked by the thermal protection system. So these ion sensors can actually distinguish between different ions, and this is useful for uh, distinguishing mechanisms and such. And then so since they can't see over the TPS, for that they have the solar probe cup, which is something called a Faraday cup, which is simply something for collecting ions within the solar wind, within a vacuum. And this uses a voltage on one of the mesh grids that you can see on the right, which will select for the velocity of the particles which can make it through. So these are, another one is the Integrated Science Investigation of the Sun, ESIS. It has two these are for more energetic particles, so from specific solar events. These measure the high and low with both higher and lower variance. So the low one, all of those knobs that you see on it are viewfinders that can intake electrons. And by measuring the time it takes to go through the detector, it can distinguish between carbon, oxygen, neon, magnesium, silicon, iron, and helium-3 and helium-4. So the high version uses a similar suite of detectors, but it has 3 layers and they are segmented, so this gives it a sense of direction. And by using the 3 layers, it can also determine different types by how much energy they deposit at each layer and such. So the wide field imager is the only imaging apparatus on the probe. It has 2 telescopes with their fields of view shown in the bottom left. And they look over the TPS and use it as a chronograph in order to image the solar wind in the corona, and a simulated view of what they would see is on the right hand side. So the final set of instruments is the fields instruments, it has 4 antennas which measure the electric fields out front. You can see them here, and then it has one here as well that that gives it a sense of depth and that third spatial dimension. So then it also has search coil magnetometers and flex gate magnetometers. These measure the magnetic field, and both are tuned for different instances. So the flex gate is more preferably tuned to further out, and then the search gate or the search coil has a higher sampling rate, which will make it better for up close when the magnetic field will be shifting lots. So because you're measuring both the electric and magnetic field from this, you can calculate the Poynting flux, which is the energy flux of the field of the electromagnetic field. So far it's still early on in the mission. So right now it's only reached up to around 30 solar radii, but eventually it will get much closer, up to, as before, around 10. So far data has been published for the first 2 encounters at the maximum perihelion distance, and so that's what we'll go over next. So one thing that they found is magnetic field switchbacks. So I'll play the image or the video to give you an intuition for it. So you can see those bends are meant to be the particles flowing along the magnetic field as a visualization for it. So what is happening is, if you look on the bottom on the first plot, each interval has many magnetic field measurements only in the radial direction. So what's happening here is, so in each time interval, these cubes or these squares on the time axis, you can see there are many measurements. So the relative occurrence rate of each of these magnetic field measurements gives how much each of these magnetic field vectors is measured. So what is happening is, you can see around the middle of the plot that there are measurements both above and below the 0 axis, so both positive and negative magnetic fields, and this this means that the magnetic field has been changing polarity during this time. And one reason this would be because it's simply passing through 2 oppositely charged or 2 oppositely polarized magnetic field lines, either going away or to the sun. But because there is something called strahl, which is electrons the majority of electrons traveling away from the sun follow the magnetic field lines away from the sun regardless of the polarity. So in the second plot below that, what you can see is the angle these electrons make with respect to the field lines. So you can see at the top of the plot is very dark, which means that there's a high amount of electrons at that angle. And if the magnetic field lines were switching, if it was 2 separate magnetic field lines that went in opposite directions, we would simply expect the angle between them to change from 180 degrees, which is at the top of the plot, to 0 degrees, as in either case the electrons are flowing away from the sun, but in opposite cases the electrons can either be pointing, or the magnetic field can be pointing away or to the sun. But because the angle doesn't switch of the straw, then this suggests that the electrons are flowing and following the magnetic field as it changes, which suggests it's a switchback, rather than two separate magnetic field lines. And then more evidence from this is from the time differences between different velocity particles. They can estimate the distance to what accelerated them, and this distance has been estimated to be larger than what you would expect from the Parker spiral mentioned earlier. So some smaller findings are small solar energetic particle events. These small events releasing lots of high energy particles are more common than we thought. This is simply because we can measure them at the Parker Solar Probe, and then we do not detect them farther out. So, yeah, simple as that. And then the solar wind is also more turbulent, as seen from, say, the switchbacks before, as well as these greater number of solar energetic particle events. So the plot on the right is suggestive of a predicted dust-free zone, which is, as you get closer to the sun, the energy will increase, as you know, so it is predicted that at a certain point, this would simply evaporate all the dust, causing a dust-free zone. So the main part that you want to look at on the right is at the left-hand side of the graph at the top. You can see the different intensities of the corona, which in this case is the corona only corresponding to the dust, and the elongation is close to the sun. So smaller degrees, smaller angles are looking more directly at the sun. So as the probe gets closer, the intensity decreases at lower elongations, which suggests that the density of the dust goes down, and hence the density is moving towards this dust-free zone, which has not yet been detected, but potentially could be. And then another small discovery is magnetic islands, which are a set of helical field lines wrapped around a central region, a central guiding field line, which sort of form a bottle, if you will. And these had been predicted before, but had not been observed at this point, and even I don't think they were saying they had directly necessarily observed it, but they were saying these are consistent with the magnetic islands. And some other findings just not mentioned here was that the distance at which solar wind begins to flow, because the corona rotates, so the distance at which it stops rotating and becomes straight as we measure it out here at Earth was unknown, or yes, unknown. And so far their measurements have found that it still continues to rotate with the sun at much farther distances than initially anticipated. So just as a closing remark, this is Dr. Eugene Parker watching his probe launch into space. It had been 60 years since he predicted the solar wind in 1958, and despite large amounts of opposition from colleagues, and now at 92 years old, he gets to witness his probe go into space, being the only living individual to have a NASA mission named after him. So it's a pretty cool way to end it.